Hi everyone, my name is George Marcu and I'm an associate professor at the Civil Engineering Department of the University of Pretoria. I received my PhD title from the National Technical University of Athens in the field of computational mechanics. I worked as a professional civil engineer in different countries before and during my academic career, while I joined the University of Pretoria in 2018. I'm also the software architect of Recon and FAIR, a finite element analysis research software. Today, I will talk to you about the main research activities of my team and the opportunities that are offered to future postgraduate students and researchers that would like to join us. The main objective of the research activities of my team is to provide our world with the tools needed towards establishing a safer and sustainable built environment. In order to achieve this goal, research work is performing advanced numerical modeling, machine learning algorithms, and experimental testing. Research that takes place in collaboration with renowned universities across the world. Students and researchers that work under my supervision not only gain deep knowledge and experience with computational mechanics subjects, but also get the chance to develop advanced skills in the area of earthquake resistance design of structures, where the design and assessment of retrofitting and strengthening is also extensively investigated. One of the main research interests of my team is the development of advanced numerical tools for the investigation and assessment of structures under extreme static and dynamic loading conditions. As you can see, this is the animation video of a two-story reinforced concrete frame under extreme cyclic loading conditions. The von Mises stress contour indicates the areas of damage during the cyclic loading. According to the nonlinear analysis, the frame was found to develop enhanced hysteretic behavior. When using Recon and FAIR, a researcher has a significant advantage that derives from the computational efficiency of the developed algorithm that exhibits numerical stability and robustness, allowing this type of analysis to be performed within minutes. This is also the reason why the investigation of full-scale structures through the 3D detailed modeling analysis is now computationally feasible. Like in the case of a 4-story reinforced concrete building that was retrofitted with infill shear walls, carbon fiber reinforced polymer sheets, and tested under 3 different levels of seismic excitation. Animation of the von Mises strain contour can be seen as it resulted from the nonlinear cyclic analysis. The cyclic nonlinear solution algorithm required a total of 8,124 internal iterations to solve this numerically demanding problem, and a total computational time of 47 hours. Another extremely demanding problem is the prediction of the shear capacity of reinforced concrete beams without stirrups. The Toronto shear panel, which was a large-scale experiment of a 4-meter-tall beam, was numerically solved under cyclic loading conditions, accounting for the loading and unloading of the specimen. The crack pattern animation can be seen as it resulted from the nonlinear analysis. It's easy to observe that the developed algorithm has the ability to capture phenomena such as the opening and closing of cracks and material deterioration, where the crack pattern predicted by the numerical simulation was found to be in a good agreement with the experimental data. In order to demonstrate the abilities of the software in analyzing large-scale models with robustness and numerical stability, this 100-meter span reinforced concrete bridge was analyzed under cyclic loading conditions. The crack pattern animation illustrates the optimum numerical handling of the thousands of opening and closing of cracks at each displacement increment. This shows that a postgraduate student or a researcher that would like to perform full-scale assessment of bridges and investigate different retrofitting methods, they now have the ability to do so. Referring to retrofitting methods and the assessment of the efficiency of strengthening, the algorithm has the ability to simulate the mechanical response of reinforced concrete structures retrofitted with carbon fiber reinforced polymer sheets. This is a model that was developed to capture extreme nonlinearities of a retrofitted reinforced concrete joint that was designed to exhibit significant cracking and slippage. This is the comparison between the numerically derived curve and the experimental data. It is important to note that this modeling method was also applied to full-scale structures for the investigation of the optimum retrofitting design, a very interesting research subject for those that would like to get involved with the strengthening of existing buildings and bridges. Currently, there is a significant amount of work performed with artificial intelligence and machine learning algorithms in developing design formulae. A work which is currently under review foresaw the development of a large database of numerical results from reinforced concrete beams without stirrups. This database was then used to train a predictive model that was then validated through the use of actual experimental data. The same approach was used to develop predictive models for the case of deep beams reinforced with FRP bars. It was found that the developed models exhibited higher accuracy in predicting the shear capacity of reinforced concrete beams compared to existing design formulae. Furthermore, the model algorithm of Recon and Fea was used to generate a database of fundamental periods for different structural and soil geometries. This database was used to train models and develop a new fundamental period formula that accounts for both cases with and without the effect of the soil structure interaction phenomenon. We are currently looking for a postgraduate student that will undertake the task of increasing the current database through additional analysis, extending the spectrum of structural geometries and types that the proposed formula is valid for. We also plan to take into account the contribution of infill walls, while further validate the ability of the proposed fundamental period formula to predict this dynamic feature of our structures. Another significant activity of our team is the investigation of the soil structure interaction effect on different types of structures. Recent work that is currently submitted for publication investigated the SSI effect when analyzing wind turbine structures founded on soft soil. The investigation foresaw the study of inclined piles where the optimum inclination was found to be 10 degrees. Additional research work can be performed in this scientific area by investigating different wind turbine tower geometries, soil profiles, and foundation systems. In addition, the nonlinear dynamic analysis of full-scale structures is a research objective that can be undertaken by a future postgrad student. Furthermore, my research team is planning to develop the required tools for creating smart monitoring systems that will foresee the use of real-time data that will be used to provide real-time models with the ability to perform risk assessment analysis. This is a very challenging but extremely interesting project for PhD and postdoctoral candidates that are interested in joining us. We are currently looking for candidates that will be involved with the monitoring and assessment of structures through the use of virtual reality technologies, state-of-the-art modeling, and digital twinning. Before closing this short video on the advantages and opportunities that a future postgraduate student or a researcher will have by joining our research team, it is of significant importance to show our new state-of-the-art civil engineering facilities that were recently constructed here in Pretoria. Our Engineering for Facilities, which is a new building that we recently constructed, will provide our current and future postgraduate and research students to perform their work in the best facilities found currently in the African continent. This is the part of the concrete laboratory, which has a hard floor, ideal for large-scale simulations and experiments on reinforced concrete structural members and structures. As you can see, this is a part of our concrete lab where our research students perform their work on reinforced concrete structural members.